This video is over lessons 31 and 32. Lesson 31, areas of rectangles, and lesson 32, expanded notation, and more on elapsed time. Take a few moments to copy down these titles into your notes. Pause the video if you need to. Moving on in 3, 2, 1. This segment here represents a unit. Could be any unit of measurement. Could be 1 inch, could be 1 centimeter, 1 mile if we're really zoomed out, 1 kilometer, 1 yard, or many other things. This square then represents a square unit. Usually abbreviated as SQ. And so for each of these units, we have a square unit. Now, what you should notice here is that a single unit by itself is going to measure a distance. Think about putting out segment after segment after segment after segment. It's going to measure a distance. However, a square unit is going to measure a surface, an area. Imagine taking these and putting them out and seeing how many you could fit across the surface. So what we see here is square units measure area. Moving on in 3, 2, 1. So if we wanted to find the area of this rectangle here, we would need to think about how many square units could we fit on this surface. So if we imagine lining up as many squares as we needed until it filled this, we could count them and find the area. And it turns out we could fit this many. So if we count across 1, 2, 3, 4, 5, 6, 7, there are 7 boxes across here, and 1, 2, 3. If you arrange them like this, 7 across, 3 down, then it's a simple matter of 7 times 3 to find out how many there are. So 7 times 3 is 21, so this must be 21 square units. And out in front here, to symbolize area, we're going to use a capital A. And so in this problem, my answer is 21 square units. And we use the word units as a placeholder until we figure out what units there are here. If these are centimeters, then later on we'll replace units with centimeters, and it'll be 21 square centimeters. If later on we find out it's inches, then my final answer will be 21 square inches. Moving on in 3, 2, 1. So in general, the distance across on a rectangle we call the length, symbolized with a lowercase l, but since lowercase l's can sometimes look like ones, we're going to write it in cursive. And then this distance here is known as the width, and we use a lowercase w for that. And so the area of a rectangle follows the formula A equals LW, or as you've probably memorized it in a past class, area equals length times width. Moving on in 3, 2, 1. So let's apply this to an example. Let's say we had a figure where the length is 6 inches and the width is 5 inches. Well, we know that area equals LW, length times width. So here, the length is 6 inches times the width is 5 inches. And so if we multiply, we find the area. Well, 5 times 6 is 30, and inches times inches gives us the square inches that we're looking for. So our answer would be 30 square inches. Moving on in 3, 2, 1. Expanded notation is a way of writing a number as the sum of each non-zero digit times its place value. So for example, let's say we had the number 1034. We could rewrite this as the sum, so we're going to do a lot of adding, the sum of each non-zero digit, so in this case 1, 3, and 4, times their respective place values. So we're going to start with 1. 1 times its place value. Well, this is the ones group, or the base group, so this next group would be the thousands. So this will be the thousands place. And I'm going to put parentheses around that just to keep it together. Now don't forget that we're finding a sum. So plus the next digit. Well, the next non-zero digit is 3 times its place value. Well, it's in the base group. This is the ones place, so this is the tens place. So 3 times 10. And then it's still a sum, so plus. And then my final digit, non-zero digit, is 4 times, and it's obviously in the ones place. So this is expanded notation. On the homework, I imagine you should be able to go a bit faster. So let's do one more a little bit quicker this time. Let's go 605,072. The first non-zero digit is 6. And if I take a look at my groups, this is the ones group, or the base group. This is the thousands group, and this is the millions. So this would be the millions, 10 millions, 100 millions place. So 6 times 100 million. Plus the 5 then, still in the millions group, is in the 1 millions. So 5 times 1 million. And I ran out of room here, so when that happens to you, what I'd like you to do is come down about even here and just go in a little bit and put your next plus sign. And keep going. So our next non-zero digit is the 7, which is in the tens place. And then finally the 2, that's in the ones place. And there it is in expanded notation. Moving on in 3, 2, 1. To go from expanded notation back to standard notation is actually quite simple. And there are 2 different ways that we can do it. So let's take a look at an example. So if I have 7 times 10,000 plus 8 times 1,000 plus 4 times 100, I can change this back into standard notation, meaning just a normal number that we're used to, by just working this out as an order of operations problem. But that's the slow way. The faster way is to keep in mind that that expanded notation means that each of these is a digit times its place value. So that means my largest place value is going to be the 10,000s place with a 7 in it. So let's just start with a 7. Now if that's in the 10,000s place, that means that the 100,000s is empty, but I need to have something in the thousands. Well, I have an 8. So there's my thousands group, followed by a comma. Now I'm on to my base group, or my ones group. So I have hundreds place, tens, and ones. Well, in the hundreds place should be a 4. And then my expanded notation ends, meaning that the rest of the digits must be zeros. And there it is. Let's do one more example. So, to figure this out, again, we start with the largest digit, which is going to be a 3. And that 3 is in the millions place, which means that in the millions group, I've got a 3, nothing, and nothing. So I'm done with the millions group, put a comma. Next, after the millions group will be the thousands group. And there's going to be 100,000s, a 10,000s, and a thousands place. So 3 places in that group. So if I look for what's in the 100,000s, well, there is something in the 100,000s. It's a 5. After the 100,000s, though, should be the 10,000s. So if we take a look here, there is nothing in the 10,000s place. So we fill it with 0. After the 100,000s and the 10,000s, I'm going to have just the thousands place, which there it is. So I'm going to fill that in with a 7. And there's my thousands group. So, comma. On to my base group, or my ones group. There's going to be a hundreds, a tens, and a ones place here. So if I look for the hundreds, nothing. But in the tens, I've got a 6. So nothing for the hundreds, 6 for the tens place, and I'm done. So fill in the ones with a 0. And there it is in standard notation. Moving on in 3, 2, 1. Our final concept is elapsed time. When working with times, you need to remember to add or subtract 12 hours when crossing over from 12:59 to 1. Numerically speaking, if we moved on from 12:59, we should go up to 13 o'clock, but we don't have a 13 o'clock. It goes down to 1, which is a loss of 12 hours. So remember to add on your 12 hours or subtract your 12 hours as needed. So let's start by calculating how long a school day is. We start school at 8:45 in the morning, and it ends at 3:30 in the afternoon. So remember, we have to keep in mind to add on or subtract 12 hours as needed as we cross over from 12:59 to 1 o'clock, which we certainly do, moving from AM to PM. So to find this, we're going to subtract. And it's going to be the time that we finish at minus the start time. So we finish school at 3:30 p.m. and we start at 8:45 a.m. Now I'm going to come over here and add on my 12 hours. So 3 is the hours place here, plus 12 is 15. So this is more like 15:30 minus 8:45. Now, as we look at this subtraction problem, we got a little bit of an issue. 30 minutes minus 45 minutes just isn't going to work. And this colon here is to separate these because these numbers here are not the same as this. The place values do not continue. We got two separate groups of numbers. Here's a ones place, here's a tens place. This is not the hundreds place. It's the ones place, but the ones place of the hours. So we got to keep that in mind. So when I realize I've got a problem here, I still need to borrow, but I'm going to borrow from the hours. So my 15 hours is going to become 14 hours. But then over here, this is not going to turn into 130. We need to keep in mind that these are hours and these are minutes. So 1 hour is 60 minutes. So we already had 30 minutes. Now we've got 60 more. So it goes up to 90. In case you missed that, the 90 came from the 30 minutes we already had, plus the 1 hour, which is 60 minutes, that we just borrowed. And that's where the 90 came from. So now we can subtract 90 minus 45. So subtraction is going to work like normal now. So borrow from the 9 makes an 8. 0 becomes a 10. 10 minus 5 is 5. 8 minus 4 is 4. And let's bring down the colon. Subtract the hours. 14 minus 8 is 6. So how long is a school day? 6 hours and 45 minutes. Moving on in 3, 2, 1. Now let's try another example. So this time our start time will be 7:52 a.m. and the finish will be 10:02 a.m. So we start with the time we finish and we subtract the time we started. Now, since it never crosses over from 12:59 to 1 o'clock, we're all set to subtract. So if we look here, there's 2 minutes here and 10 hours there, 52 minutes there, and 7 hours here. We cannot subtract 2 minus 52. So we need more minutes, so we're going to borrow. So I borrow 1 hour from the 10 hours, making it a 9. And so my 2 minutes are going to get a whole extra hour. So 2 minutes plus an extra hour, which is 60 minutes, is going to turn this into 62. And now we're ready to subtract. 62 minus 52 is 10. Bring down the colon. And 9 minus 7 is 2. So how long is it? 2 hours and 10 minutes. Moving on in 3, 2, 1. This time we're going to do a slightly different example. Let's say we start at 11:51 a.m. and we want to find out what time would be 5 hours and 37 minutes later. So since we're going later, we're adding on time. So we're going to make an addition problem. Start with our time, 11:51 a.m. And now we're going to go 5 hours and 37 minutes later. So 5:37. And we're ready to add. So let's add up our minutes first. So 1 plus 7 gives me 8, and 5 plus 3 also gives me 8. Bring down the colon. 11 plus 5 equals 16. And we'll go ahead and bring down the AM for right now. So if we think about this answer, it doesn't really make sense. There's no such thing as 1688 AM. First of all, we have too many minutes. So what we're going to do here is we're going to shift some things around. So I'm going to take 60 minutes off, and it's going to make 1 extra hour. So I'm going to have 1 more hour, so 17 hours. And if I take 60 off, so 88 minus the 60 minutes it takes to make an hour, is going to leave me with 28 minutes. But 17:28 AM still doesn't make sense. And this is where we need to keep in mind when crossing over from 12:59, it should become 1 o'clock. So going from 11:51 to 17:28 would cross over. So this time we need to subtract 12 hours. So 17 minus 12 gives me 5. And since we crossed over from 11 to 12, of course this is going to change to PM. Moving on in 3, 2, 1. For our final example, we're going to take a look at what if we finish at 4:25 p.m. and we want to find a time that's 2 hours and 45 minutes earlier. Well, if we want to go back in time, it's going to be subtraction. So we start again with our time, 4:25 p.m., and we are going to subtract 2 hours and 45 minutes. So if we look at the minutes, 25 minus 45 is not possible. So we're going to need to borrow. Borrow 1 hour from 4, that makes it a 3. And I already have 25 minutes, and I'm adding on an hour, which is 60 minutes. So therefore, the 25 minutes is going to become 85 minutes. And now we're able to subtract. 85 minus 45 is 40, and 3 minus 2 is 1. So what time would it have been? 1:40 p.m. And this video ends in 3, 2, 1.